All right, welcome to our first video for AP Physics 2. Now, AP Physics 1, what we did was we studied basically mechanics. We studied kinematics, forces, energy, momentum. We studied circular motion. We studied gravitation, simple harmonic motion, and then we studied rotational motion. What we're going to do in AP Physics 2 is to look at all of the very interesting physics topics that weren't covered in mechanics. And actually, the rest of it, there's some really, really cool stuff. You might think, hey, we did a lot of stuff with motion last year. We're going to look at some stuff that is totally different this year. We're going to cover fluid mechanics. We're going to cover thermodynamics. We're going to cover electricity and magnetism in almost its complete form. We're going to cover modern physics, which is basically nuclear and atomic physics, and we'll even cover some optics. So there's a lot of stuff to get to this year. We're going to start with fluid mechanics because it has a lot of analogies back to your mechanics knowledge. So that's how we're going to start. Last year we focused on solid objects for the most part. Fluids are obviously not solid objects. When we talk about fluids, we mean either liquids or gases. Mostly we'll be talking about liquids, but in a couple cases we will talk about gases. And when we talk about thermodynamics, we'll pretty much just be talking about gases. So with liquids or gases, they have no fixed shape or long-term arrangement of their atoms. That's why they don't have a fixed shape. Okay, that's all we mean by fluids. Usually, it means either a liquid or a gas. Usually we're going to be studying, when we talk about fluid mechanics and fluid dynamics, we're pretty much talking about liquids, but every once in a while we will mention gases in there. We are going to primarily deal with what we call ideal fluids. In an ideal fluid, have the following four assumptions. First, we're going to assume what's known as steady flow. In other words, the velocity of the flow at a certain point is constant. As opposed to non-steady flow, which would be the velocity at some point in that fluid flow is changing over time, either chaotically or over some certain rate. Okay, so an example might be like imagine a nice steady flowing river that the water is moving at a certain speed the entire at any point consistently. Non-steady flow would be like rapids, which has a lot of chaos and turbulence in it. So steady flow is one assumption. We're also going to assume incompressible flow. Which means that not only is the speed constant over time, but the density of the fluid is constant over time. We are going to assume non-viscous flow. Viscous here referring to a term called viscosity. Basically what that means is we are going to ignore any internal resistance to flow. This is sort of like friction. We're not going to really talk much about viscosity, but to give an example, water is very non-viscous. You can almost think of it as the water doesn't like stick together. Okay, water moves smoothly over the other water. A viscous substance would be a substance that it's like sticks to itself. Think of like how syrup or molasses works. Those are viscous fluids. It takes a lot, like objects moving through those fluids really get kind of like there's resistive forces. Objects moving through water, it is viscous, but it's not nearly as viscous as those liquids. And then finally, our last assumption, and this one really does not come up until you get into much higher level physics, is irrotational flow. And basically what that means is objects don't spin due to the influence of the liquid. Or influence of the fluid, I should say. Okay, and those are our assumptions. We won't talk about them much. We'll talk about mainly the incompressible part, the fact that the density is the same over time for the fluid, and also steady flow. Those are the two most important. We'll talk about the viscosity maybe once or twice, but it's not going to be a normal feature. Okay, so I've already kind of mentioned one of the terms that we're going to talk about that's very important in fluids, and that is density. Now we know that when we talk about solid objects, we discuss mass. That doesn't make as much sense for fluids because it's a whole bunch of little particles spread out over some space. With fluids, it makes much more sense to talk about density. The definition of density is mass per unit of volume. The symbol for density is this kind of funny looking P. It's a P, but its tail is kind of curving under. And it is the Greek letter rho, R-H-O. So density, rho, equals the mass divided by the volume. Hopefully you could have got that from this definition up here. The units are kilograms over meters cubed. And density is a scalar. Okay, you've studied density before at lower levels. I'm not going to spend much more time talking about density, but it is important to know there's one density that I do want you to memorize. Okay, I almost always, and the problems will almost always give this density to you, but I think it's a good idea to remember what this number. The density of water is just about, and this is pure water, by the way, not salt water, fresh water, 1,000 kilograms per meter cubed. Okay? All right. Now, pressure. Because fluids have no set shape, they can exert forces over an extended surface. Okay? Because they don't have any shape, they can fluids will spread out and they can exert force over some surface. So instead of talking necessarily about force with fluids, we can talk about that, and that is useful. It's also useful to talk about the pressure. And the pressure, which is symbolized by lowercase p, now you are going to have to be able to tell the difference between lowercase p and this rho thing, okay? They do look different, they're always written different, but make sure you understand the difference between the two of them. We're not talking about the same thing here. P equals F divided by A. In other words, the pressure on something is equal to the force applied to that object divided by the object's surface area. So F is force applied. And we don't have to think of it as an applied force. It's just the force that's acting on some surface. And then A is the surface area that the force is applied to. The The units for this are newtons per meter squared, or what are called pascals, which is symbolized PA. And this is actually scalar. Another important thing that's, I think, good to memorize, but this is on the reference tables. This first one is not on your equation sheet for this year. This is on your equation sheet. Well, actually, it's a very slightly different number. Air pressure we experience at ground level on Earth. There's another unit of pressure that we call atmospheres. 1 atmosphere, or another symbol for that is ATM, and that is equal to 1.01 times 10 to the 5th pascals. In other words, 101,000. 101,000 pascals. Okay, so that's important to remember, that this is the standard air pressure just due to the atmosphere. Now, we've got the basic definitions of density and pressure. I want to spend some time talking about depth and pressure. In other words, how does pressure change as you go, as an object moves lower in some liquid? We're going to do kind of a hypothetical situation here. Let's say that we have a large container of a liquid open to the atmosphere. Okay, so I'm going to draw it over here. Here's our container of liquid. Great. Now we're going to take an arbitrary, that means the volume doesn't really matter, an arbitrary volume means it could be a very big volume, could be a very small volume of water. Let's say at that volume's top edge is at the surface, or an arbitrary volume of, I shouldn't say water, let's say liquid. Top edge at the surface. Top and bottom faces of equal area, and all right angle sides is shown. And also there's a free body diagram for that. So we're going to draw that in right now. What I'm saying is, let's take, here's our arbitrary volume of water. You can imagine that it extends into the page. We have a top surface and a bottom surface that are of equal areas, and every angle between the sides of this imaginary shape, volume are at right angles to each other. A free body diagram for this liquid might look like this. Oh, I guess 2 more assumptions. Assume a still liquid, and that up is positive. So here's our volume of liquid. We're going to say up is positive, and we're going to write out the forces that are on our imaginary volume of liquid here. Well, we know that this imaginary volume of liquid is in contact with the liquid that's below it. Okay. By the way, we're only going to deal with the y direction here, and you'll see why in a second. There's some liquid below this, and because our imaginary volume of liquid is in contact with this liquid below it, that means that the liquid below it puts a force, an upward force, on our imaginary volume. So I'm going to call this the force from below. It's also in contact with the atmosphere, which is going to push down on it, so I'm going to do F atmosphere. And if you think about it, this volume of liquid has some mass. And if it has mass, that means that there must be some force of gravity on it. So we're going to have Fg. So my net force equation, assuming the liquid is still, that means it's not moving up and down. And if it's not doing this over a long period of time, it's not accelerating up and down. The net force equation might look like this. F net y equals the force from below minus the force from the atmosphere minus Fg equals MAY. And we're saying, let's assume that that's 0. We're going to recall a couple of things. We know that forces are related to pressure. Remember, this is a liquid, so we really want to talk about pressure and not necessarily forces, because we have this kind of extended area that the liquid below can push up on our imaginary volume of water, or volume of liquid with. So we have a force, but we can change this. We can rewrite this force into something in terms of pressure, because we would know that force is equal to pressure times area. So here's what I'm going to write instead. I'm going to write P below, in other words, the pressure from below, times the area of that imaginary volume, that side right there, minus the pressure from the atmosphere, times that area, which is the same, okay, we said that, equals mg. Now, I'm going to change these because I don't want to keep writing below an atmosphere. We're going to change this to the pressure from below. We're just going to call that PA minus pressure from the atmosphere. We usually call P naught A equals, and let's remember the density equation. Density is equal to mass over volume. So the mass is equal to the density times the volume. So let's see here. Instead of writing mg, I could write rho times the volume that we're dealing with here of this object times g. And we're going to make one more change. Remember, the top and the bottom faces are both A, and if that's true, then the volume of this box, of this imaginary container of liquid, can be described as A, the area of the top and the bottom, multiplied by H, okay? Because I would find the area of this side down here, I multiply by H for the volume. So I could rewrite this as PA, the pressure down here from below, at the below surface, minus P naught A, the pressure of the atmosphere up here, equals rho A H G. Notice what I've done. There's a reason that I've written it like this. I now have an A in each term, and those A's all mean the same thing. So I'm going to cancel, cancel, and cancel. And I'm going to rewrite this a little bit. I'm going to rewrite this like this. P equals P naught plus rho G H. And I'm going to define these terms over here. P is equal to the absolute, or in other words, the total pressure. P naught is equal to the atmospheric pressure. Okay, and that rho GH term is equal to what we call the gauge pressure. And in other words, that is the difference between the atmospheric pressure, or excuse me, the absolute pressure and the atmospheric pressure. It's called gauge pressure because if you were to take some sort of gauge or take some sort of monitor and read what that pressure is, what rho GH was equal to, that would be, rho GH would be equal to whatever your little sensor would tell you. Okay. So what we see here is that the pressure increases linearly with h, which we defined as the height of our imaginary volume but if you look at our picture, it's also equal to the depth below the surface. And that's the interpretation that we're going to use. In this equation, P equals P naught plus rho GH. P is the absolute or total pressure. P naught is the atmospheric pressure. Rho is the density of the liquid. G is acceleration due to gravity. And H is the depth below the surface. So if you want to know the absolute pressure at a certain point below the surface, all you have to know is, or all you have to use is this equation. You just have to know how far below the surface we're talking about. One thing I want you to notice, which is very important, is that this pressure is only dependent on depth. And it's not dependent on horizontal position. And that will come into play a lot later on. I want to very briefly talk about two different ways that we can measure different types of pressure. The first one is atmospheric pressure. And that's measured by a barometer. I'm going to draw a very, very simple barometer to start off here. Oh, there we go. Let's make that a little clearer. Okay, I'm going to draw a very, very simple barometer. Get that out of the way. So we're going to have a container of fluid down here. And we're going to have a tube that is in this container of fluid. Usually the fluid that we would be using is mercury, by the way. Okay, so this represents the level of the mercury in our container. And what you'll notice is, depending on the atmospheric pressure, the mercury will be pulled up into this tube to some level. All right. So the way this works, you have mercury in some glass tube, which is in some wide container. Now, right here, the pressure at the air-mercury interface is the atmospheric pressure. P naught. The pressure in the tube just above the mercury is approximately 0 pascals. And that's because we need this to be a vacuum. There's nothing up here besides mercury vapor, and there's so little mercury vapor that the pressure is essentially 0. Essentially, it's in a vacuum. If we have this set up, P naught, the atmospheric pressure, can be calculated by being equal to rho GH, where H is this right here. The difference, not all the way down there. Sorry, that's a little misleading. Where H is the difference in the levels of mercury. In other words, the difference in height between the level in the tube and the level in the dish. And again, that works because we know that as we go down through a liquid, the pressure should increase. And pressure is not dependent on any horizontal variable. So in other words, the pressure here on the sides of the tube is equal to the pressure right here. So if we know that this is atmospheric pressure, we can tell what that atmospheric pressure is because we know this pressure up here is 0, and since the atmospheric pressure in this case is equal to rho GH, since this is 0, we go down here a distance h, and therefore we can calculate using rho GH our atmospheric pressure P0. I'm going to stop it there. We'll come back and look at one other way to determine pressure, and then we'll move on to talking about Pascal's principle and the buoyant force.